Welcome everyone. Today we are going over section 1.3 part 2. We are doing a proof example, and in this proof example we are not using truth tables. We're using logical equivalences. Just a recap of the last part 1 video. We learned about tautologies, what one is. It's basically a composition of two propositions that is always true. Let's see. Example is not P or P. If you don't understand this, you just watch the last video. I went over this in a very good detail. A contradiction is the same thing. It's a composition of two propositions as always. Always. It's the opposite. It's not the same. It's the opposite. So it's always false. So example is the same. This part is always false. Example not P and P. So it's the complete. These are like total opposites. We also learned what this means. This means equivalence. So it means that like the truth table values are the same. If you wrote out the truth values, there's two ways to prove equivalence. So the first way is using truth tables. So you look for make sure that all the values in each column are the same. We went over an example of that in the last video in part 1. And today we can also prove it using logical equivalences. And so logical equivalences are, I showed this in the last video, it's these, and we use these to prove equivalence, to prove that in the second way. So we're doing that type of example today. Also, these are also two other logical equivalences you must know. We're not going to use them today, but in a majority of proofs that you're going to see on tests and all that are going to use these. So this just make sure you memorize these. And the other ones you kind of just more practice, it kind of comes naturally. So today, let's start our example. We are going to prove this. Let me write it out real quick. Not P and not Q. So usually when you do this, we can either use truth tables or we can use logical equivalences. Sometimes, a lot of times, like teachers will be like, you can't use truth tables, you have to use logical equivalences. So usually want to take the bigger one and convert it to the smaller one. That's usually kind of how it goes. It's easier. But we're basically going to manipulate these different ands and ors and nots with the different laws that we learned in the last video, the logical equivalence laws. I would just, if you don't have this like that, you could just print it out and have it next to you when you do these. And then you kind of turn this into that, turn this into that. So we're going to start out where you write out the bigger one. You write out the bigger one, and you say it's equivalent to, and you have reasons here, or reasons can be over here. So first we use De Morgan's law from, remember we're using this chart. So just take a second, screenshot it, print it out, look at it while we're doing it. So take this not and put it, like, distribute it onto these things. So when you do that, this will turn into not P, this will turn into and, this will turn into P because it's like a double negation law. So basically you distribute the not through, so we say it's equivalent to not P and then you can use, you put it right here, put it on the outside, so we can do it in multiple steps. So we distributed this into this and onto this. Now we write down again, so we use De Morgan's, and then we distribute this not onto this little section here, so not P, and these cancel out. This is called the double negation law, so it just turns into P or not Q. This is also De Morgan's. Then these are the reasons why. So then here's this. Now we need to basically open this up. So like we use something called I believe it's called the distributive law. So you can write it like using the distributive law, use it's not P and P or not P and not Q. So this is called distributive. So basically take this and distribute it to this and this. And when you do take this and distribute it to this and this, it becomes that. You follow the example of the law. And then we learned in the last video, the first thing we talked about was a tautology and contradictions. And this is an example I showed you, not P and P. So to write that out as a contradiction, you write like a bold F, kind of bold it with your pencil or pen, or not P and not Q. So we can say we used contradiction here. Now, anytime basically we want to use this thing called an identity law. Basically, identity, let me write it here. The identity law was P or false, and that's a bolded F. Gives you back P, like equivalent to P. So whatever you put in the proposition here, or contradiction, gives you back the proposition. So we have this, so it gives us back this proposition. Well, I mean, you could flip it, but so basically using community, what's it called? I believe you can, there's a law that this can be written first. It doesn't matter which one's written first, whatever's on either side of the or. You can write this over here, this over here. So it's saying it follows this pattern. It gives you back the proposition, so not P or not Q. And haha, look, so we use this law. And now, if you look, that's the same thing as this. So this is called, when you write identity law. So we were proving this is equivalent to this. You can use truth tables, or you can use proofs like this using logical equivalences. And you start out with usually the bigger one. Doesn't matter. You can probably mess with that to get to this, but you'd have to figure that out. Probably expand it a little bit. But what you can do is just take this and use these laws. First we use De Morgan's again. We put that into here for this. Then we distribute it, opened it up. Then we saw this as a contradiction. So when you write a contradiction, you put a false, a bolded false. If it was a tautology, you would put a bolded true. And then you can see that using identity law, it gives you back the proposition, and you have it. So this is how to prove using logical equivalences. And there's a bunch of, different examples or proofs, but this should get you started. So hope this is it. If you have any questions, leave it in the comments. Thank you.